Hi, welcome to this lecture on mathematical methods for biologists. Today's topic is function, derivatives and series expansion. So in this lecture, we will discuss the idea of infinite series once more and what is the idea behind the infinite series and how is it useful, what is the use of this series. So what we learned is that we learned infinite series for various functions. We learned infinite series of sine, cos and exponential function, and we have learned, for example, that e power x can be written as 1 plus, this is something that we learned, e power x can be written as 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus dot 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 up to infinity. So finally, you will have x power 10, x power 100, x power, this whole thing is e power x. Now, this kind of infinite series, where did it come from? Right? The first question is who started with this idea that any function can be kind of written as an infinite series. It turns out that any function can be written as an infinite series like this. Any function. And this is very useful in general for science, also in biology, because many things that what we want to know in sciences and in biology, if you want to know, for example, concentration as a function of x. So for example, you want to know C of x. So you want to know concentration at some point x, if you know some other information, or we want to know energy as a function of x. At some particular x you want to know energy, or you want to know the position as a function of time. So this is concentration, energy, position. So we want to know all of these functions. If we know some ideas in mathematics, can we guess this function? Is it useful to understand these functions? These are the questions that would come to anybody's mind. Can I know this function? Can I know the energy function just like that by knowing some ideas from calculus? Can I guess the energy function? Can I write down the energy function? Can I know the position if I know some information? Right? So this is the thing that anybody would want to know. So for this infinite series is very useful. So we would use this idea from infinite series. So idea of infinite series. So first of all, so the obvious question is, who started this idea? Where did it come from that any function or many functions can be expanded as infinite series? Right? So this is a question that who came up with this idea of infinite series? It turns out that this idea was first discovered in India in around 1400. So this idea was first proposed by mathematicians in Kerala, a part of South India and a part of India, around 1400 CE. Of course, we may not know the exact date. So, but the manuscripts that now got from Kerala, which has as old as 1400, 1500 CE, describes the infinite series of sine, cos and all that. So, there is something called, there were in around this time, the medieval times, 1400 to 1500 CE, there was a school, there was a group of scientists who now is known as Kerala School of Astronomy and Mathematics. This was a group of mathematicians and astronomers who lived in this era from 1400 CE to 1500 CE. And one of the prominent person in that is, his name is Madhava. And the place is called Sangama Grama. So Madhava of Sangama Grama in Kerala first proposed this kind of infinite series first around 1400 CE. So Madhava proposed series for sine, cos and pi. So pi can be written as tan inverse x. So you should think about how pi can be written as tan inverse x. So he first proposed, the Madhava proposed this series for sine, cos and tan inverse x, which is related to the pi. So using this idea, we don't know whether anybody else knew this idea at that time, but certainly the manuscript that we know now, we have got now, clearly shows that this was known to them, and there was detailed description of all this. So later, about 200 years later, close to 1700 CE, CE means Common Era, which is same as AD, right? So European mathematicians discovered it around 1670 in the Common Era, which is CE, which is AD. Newton, Leibniz, Gregory, they all worked independently and discovered these series, like they all discovered different series. So this Leibniz series, Gregory series, but they are all infinite series. Sometime around 1700 CE, CE is Common Era, in Europe, this was discovered. So probably this was discovered first around 1400, 1500 CE, about 200 years before Europe in India, but whether this was spread to Europe or not, we don't know precisely. But a British civil servant who worked in Kerala at that time, he was collecting manuscripts, old manuscripts from various parts of India, and when he read this, he found out this school in Kerala, Charles Wish, and from that people understood about this. And now I urge all of you to go to Google and search for Kerala School of Astronomy and Mathematics. In the medieval Kerala, it's also called Kerala School of Mathematics, which was flourished around this 200 years period from around 1400 CE to 1600 CE. There is a bunch of very famous mathematicians who did excellent work, pioneering work, a couple of centuries before what it was discovered in Europe and elsewhere. Okay, so, but what we now use as an infinite series, which is very commonly used, is called a Taylor series, and this was generalized decision of this series by a person called Brooke Taylor, a British scientist. I think it's around 1715 CE, and what Taylor found is that we can know a function at any point x. That is, we can find f of x at any point x if we know the function at some point a and all its derivative at x equal to a. So this is something very useful. We want to any function. So this is something which is very useful, and let me describe this a little bit carefully. So we want to know. So think about somewhere so you want to know the function value at this point x. We want to know the value of this function this point. If I know this function some other point, which is called a, if I know the value of the function here, can I know the value of the function here? So can I find out the value at x if I know the value at a? It turns out that we can find, and how to find this is what is the Taylor series. So the Taylor series says the following: to know the function at x, you have to know the function at a and all its derivatives at a. So if you have to know df by dx at a, you have to know d square f by dx square at a, d cubed f by dx cubed at a, d power 4 f by dx power 4 at a. If I know all these derivatives at a at this point and the function, we can calculate the value of the function at this point. So let us understand this in a different way. If I plot this, so we would typically plot x versus f of x. So at some point x, so let us say this point x, the function could have any value. So the value of the function, the y value, the value of the function could be anything. It could be here, or it could be here, or it could be here. So we want to know where this function is. What the value is here or here or here or here. What is the y value? We want to know that. So that's what we want to know, f of x. But we can know that if I know the value at some other point here, which is x equal to a. So if I know that at x equal to a the value is this, then the value here could be, the function would be here, could be here or here, it could be anywhere on this line. The next point here could be here or here or here or here, we don't know anything. We only know this value of this function at this point f of a. So we know this f at a. It's not enough to know this function at a. Of course, if I just know this point, I cannot guess where this is. I have to know the derivative, that is the slope. If I know the slope, so if I know df by dx, think about it. If I know the df by dx, what do I know? So if I know the df by dx at x equal to a, if I know that the df by dx at x equal to a is positive, then it is going to be the slope, local slope is going to be like this. The local slope is going to be like this. So that means the function is likely to go up. If the local slope is, if the function is negative, the local slope is going to be like this. If the function is, if the df by dx is negative, then the local slope is going to be like this. So then the function is going to decrease. So this, if the local slope first of all will give you the direction whether it is going to go up or going to go down, and therefore this is very useful quantity. I hope you understand this. Think about it. I know the functional point, I know this point. I also know the slope. If the slope is like this, the function is going to go like this. If the slope is like this, at least locally is going to go like this. But it's not enough to know the slope. You have to know all the second derivative, whether it is curving and third derivative and all the derivatives at this point x. That is, it's not just the slope at this point. You have to know the slope here. If you have to know the curvature here, if I know the third derivative here and all derivatives here. So slope, then the curvature at x equal to a. You know the curvature here, slope here and all derivatives. If I know all derivatives here, then I can guess the value of this function here. So it says what does it now Taylor series say? How do you get that value? So that is the Taylor series. So it says that if the function at any point x, if I know the point function at a, so if I know the value of the function at x equal to a, can I know the function at x equal to any value of x? So the answer is we can. So what does the Taylor series say? The Taylor series says we can calculate the function at x. If I know the function at a, I have to add to this value of the function something. What do I have to add? I have to add the first derivative df by dx at x equal to a. This derivative not somewhere, this point the derivative, the slope at this point x equal to a times x minus a, this distance, this minus this. So this is the point a, so x minus a is this distance. So divided by 1 factorial plus second derivative, that is the curvature at x equal to a times x minus a whole square divided by 2 factorial. So I have to take the square of the distance and 2 factorial plus the third derivative at x equal to a times x minus a whole cube divided by 3 factorial plus dot 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 up to infinity. So if I know the function at a is slope at x equal to a, its second derivative at x equal to a, its third derivative and all derivatives, each derivative I multiply with x minus a to the power n, to the nth derivative, and divided by n factorial and sum this way, I would get the function at this point. So sometime x minus a could be negative, then this will be a minus and so on and so forth. Second derivative, first derivative could be negative, second derivative could be whatever be the value appropriately. So depending on all that, you would get this answer. But this is a formula that can be used to know the function if I know the function at a. So what does the Taylor series say? The Taylor series says that f of x, the function at x can be obtained if I know the function at a. To that I add f prime a divided by 1 factorial times x minus a, that is first derivative times the difference, plus second derivative f double prime a, second derivative evaluated at a divided by 2 factorial times x minus a square, third derivative divided by 3 factorial times x minus a cube, and so on and so forth, where f prime, f double prime, f triple prime are the derivatives of function at f of x at point a. So if I know all derivatives at a, I can use this and obtain this. I could use a as 0. So I could, instead of a, I could substitute 0. Then this would simplify. Of course, f of x is f of 0 plus f prime, the first derivative is 0 by 1 factorial times x, second derivative is 0 divided by 2 factorial times x square, third derivative at 0 divided by 3 factorial times x cube. So this is an expansion at a equal to 0 is called a Maclaurin series. So one can use this. Now, if I know this, how is it useful? For example, this e power x that we learned, or any function sine of x, these are expansions like this. So let us first consider some function. So think of a function. We have to know what all things we have to know. We have to know the value of the function and all its derivatives. So let us think about some function we want to calculate, f of x. What would be that function if, what is the simplest thing we can imagine? We can imagine that the function at 0 is 1 and all its derivatives at x equal to 0 is also 1. All its derivatives are equal to 1. So this is something which we can start imagining. You know the function, so for simplicity, let us take the function is 1 and all its derivatives are also 1. If you assume this, what would we get? So let us see what we want. We want the function f of x. The Taylor series says f of x is f at 0 plus df by dx at 0 times x plus d square f by dx square at 0 times x square by 2 factorial plus d cube f by dx cube at x equal to 0 x cube by 3 factorial plus infinite dot 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 dot. So if the simplest assumption is that this is to be assumed to be 1. So I will put here 1. This derivative, let us assume to be 1. This derivative is also 1. This derivative is also 1. So let us assume all derivatives are 1. Then what do we get? We get 1 plus x square by 2 factorial plus x cube divided by 3 factorial plus x power 4 by 4 factorial plus dot dot dot. What is this? This is nothing but e power x. So e power x is nothing but a special function. It's an interesting function whose value and its derivatives are equal, all equal to 1 at x equal to 0. Right? It's all derivatives and the value, the function itself is same as its derivative, and this would immediately lead to e power x. We can have many other applications. So let us think about if we want to know the position. So let us write again once more what is Taylor series. It says f of x. If I know f0 and I know the first derivative f prime, x by 1 factorial plus f double prime evaluated at 0. So this is evaluated at 0, x square by 2 factorial plus dot dot dot. So let us take here x as time. So I would represent t So let us say what we want. We want to know the position of a particle. We want to, many things are moving. So if you want to know the position of a particle at any time t, so let us write r of t. This is what I want to know. I want to know what is r of t. What is r of t? Position of a molecule in a cell or wherever you want, or not in a cell specifically, wherever it be, position of a molecule at any time t, at any time t. If I want to know this, I would substitute f is equal to r. So x is time, f is position. So then if I want to know this, let me write r of t is r at 0. If I know the initial position at time is equal to 0, plus the first derivative, which is dr by dt. What is dr by dt? Is nothing but velocity at time is equal to 0. This is called initial velocity. Time, so x is time, plus second derivative d square r by dt square, t square by 2 factorial, which is nothing but 2. So if I use this, so if I know the initial position and initial velocity and the acceleration at t at this time t equal to 0, I can get this. If I assume all derivatives are 0, is just this. So you can see, if I can do an approximation. So what do, if I just take any Taylor series, if I just assume that, so if I consider this, if I assume x is very close to a, I can neglect all other points. So it can be approximated. If I assume x is very close to a, then higher order terms can be neglected. If I assume that x minus a whole power n is very small, that is one way. But this is a way of getting position. So think about this. This will turn out to be Newton's equations. So Newton, if you assume that acceleration is a constant and all derivatives beyond third derivatives, fourth derivatives, etc. are 0, then we will get this position expansion will turn out to be Newton's equation. So let us see here. Here x is basically the position. So x of t be a smoothly changing position function whose value at x equal to 0 is at time equal to 0 if we know. X at any time t can be written as position at t equal to 0, velocity and acceleration. You see, this will turn out to be the Newton's equation that we all learned in school. So this is one can, using this idea from mathematics, Newton's equation will naturally emerge. The only assumption here is, if you assume higher beyond acceleration all derivatives are 0, then this will be precisely the Newton's equation. So the position at any point just emerges from this simple mathematical idea. Can we use this for some other function? So of course we can use energy as infinite series. So let us think about it. What do we want? We want to know the energy of a molecule. So let us say we want to know, we have some molecule, and this molecule, these two endpoints are important, let us say. So this distance between these two endpoints, let me call x, is this distance between these 2 points. So energy of the molecule, if those 2 points are x distance apart. What is the energy of this molecule? So this molecule, which could be a protein molecule, this protein molecule could be either like this, or it could have some other conformation where maybe like this. It is expanded, it is stretched, and it could be this conformation. So in this conformation, the distance between these 2 points is very large. So here x is small, here x is very large. So you could have many other conformation. You could have a conformation where it's like this. let me draw like that, something like this, where these 2 points are very close. So this x is very small. So here the x is, the distance between these 2 points is very close. So here these two ends are very close. Here this is some distance apart. Here it is far away. So what is the energy of this molecule for different values of x? So that is the question that we want. So the Taylor series would say that if I know the energy at some other point, any point x equal to a, some distance, if I know the energy at one of these x values, if I know energy for this x value, if this configuration energy if we know, we can calculate the configuration energy for any other x by calculating the derivative of this dE by dx at x equal to a times x minus a plus d square E by dx square x minus a whole square by 2. Right? So let me rewrite this a little bit more carefully here. So if I rewrite this, energy at any point x can be written as energy at energy of some configuration A. So energy of the configuration having distance x is energy of this configuration plus derivative of energy E prime means dE by dx times x minus a plus E double prime second derivative of energy times x minus a divided by 2, x minus a square divided by 2. So if I know this is plus dot dot dot. So if I assume x is very close to a, I can neglect all x minus a cube and x minus a power 4 etc. will be very small compared to x minus a. So I can neglect it. So I can write approximately, so I can write the following that, so what do I can write? I can write E at x is E at a plus derivative E prime x minus a plus E double prime x minus a whole square by 2. So if I write this is this is approximately equal to, because I neglect higher order terms. So approximately the energy can be written as, so I can take this way and write Ex minus Ea. So that is, I can write E of x minus E of a. This is the change in energy, approximately equal to E prime, first derivative. First derivative is some constant, let me call it k1 into x minus a, right? X minus a plus k2 by 2 into x minus a whole square. So if I assume energy of this is 0 and a is 0, if I take a equal to 0 and E of a equal to 0, so if I do that, if I assume E of a is 0, I can write the energy or the delta E as k1 x plus k2 x square by 2. So this is essentially like approximate form of energy plus higher, plus in principle all infinite terms. Like this I could write, if I know this k1 and k2, I can calculate this energy. So if I just take a spring-like molecule, so if energy of a spring-like molecule, spring has a symmetry that if I compress or expand, the energy has to be the same. If I have some symmetry like this, I can say that the first derivative will be 0. So if I figure out that the first derivative is 0, the energy will be essentially some constant times x square by 2, like half kx square. So this is how the half kx square comes. But this kind of expansion is very useful for calculating energy of many proteins, and we will use this idea later. Many contexts, energy can be written as expansion of functions like this. So to stop and to summarize what we learned the idea of infinite series, We learned Madhava and Kerala School of Mathematics, how they started it. We learned about Taylor series and its applications. And we talked about applications for a position as a function of time, application for energy. You can also think of concentration at some point x. How can we calculate the concentration of some point as a Taylor series? Can we do that? I urge you to think about it. So the idea of this lecture is, can we calculate our favorite function at some point x if I know the function at some other point and all its derivatives? This idea will be used very often in various places. Think about this, and this is extremely useful. With this, I will stop today's lecture.